In this lecture, I want to talk about binomial coefficients. So that's a very fun topic which everybody likes usually. So 1.4 binomial coefficients. Okay, so we can forget about permutations for a while. We will return back to them soon. So let's start with a certain set with n elements. So let S be a set with n elements, and I will just denote the elements by 1, 2 up to n. So and then I can look at all subsets. So denote by 2 power s. That's just a crazy notation, so it doesn't mean you take actually 2 in any power. It is just a notation. You will see in a second why. The set of subsets of S. So for instance, I can take n equal to 4, and then S has, so 2 power s, sorry, n equal to 2, and then 2 power s has 4 elements. So it consists of a subset which is empty set, then 1, 2, 1, and 2. Okay, perfect. So these are all subsets of the set with 2 elements, and probably a very well-known fact which I'm going to prove is the following proposition. Which will look a little weird. So the number of elements in the set of subsets is equal to 2 power the number of elements in S. So every set has 2 power n subsets, where n is the corresponding number. Okay, so so proof, again, there are different ways to prove something like that, and I want to not only prove the proposition, but also explain sort of how to think about this 2 power s subsets. So for this, let me maybe start with example again. So let me take a set S maybe with 1, 2, 3, 4, 5, 6 elements. And I want to come up with a certain way to code subsets. So let's consider, for instance, a subset 1, 3, 5. So to each subset, I will associate a certain code. So a code will be a vector, so a sequence of zeros and ones, where I put 1 if my element, first element is in the subset, and 0 if not. So here I will get 0, 1, 0, 1, 0. Okay, so in this way I construct a map. So we have a map, so let's so consider a map from 2 power s to the set of sequences of zeros and ones of size of length n, which sends any element here, which is a subset, to a sequence which I will denote S1 up to Sn, and the rule is that Si equals to 0 if I is in the subset, and sorry, is not in the subset, and 1 if I is in the subset. So how shall I code it? How shall I name it? Let me call it f. So this is what f does to the subset. And for instance, I can compute it. For instance, f of the empty set is the vector which has only zeros, nothing is there. And if I take f of the whole subset S, it's also a subset of itself, of course it will be just the vector of ones. Perfect. And then basically the main idea is that f is a bijection. So f is a bijection. And that's really easy to see, basically because I can construct the inverse map, which takes a sequence and constructs a subset, which is just a union of elements, and basically the element is there or not, depending on the index. So that's more or less obvious, and of course this proves the proposition, because clearly the set of all subsets of length n has 2 power n elements, and basically the reason is because this set of sequences is nothing but a Cartesian product z comma 1 power n, where this is the Cartesian power. So that's the end of the proof, and this kind of a code, a way of coding subsets by sequences is very important, and it's very useful in computer science and in mathematics. And sometimes people think of this set of sequences as vertices. So sometimes people think of it as vertices of a cube, but in n dimensions. And the reason is that if you just try to draw the picture, so if you are in the case n equal to 1, then you will get just 2 points, 0 and 1, and I just think of this things as Cartesian coordinates. And if I do n equal to 2, I will get 4 points, 0, 0, 0, 1, 1, 0, 1, 1, and that gives me a square. So for n equal to 3, that will obviously give me a cube. And for n equal to 4, the problem is that now I live in 4 dimensions. So I have, so here I have 6. I have 4 indices, and so I get what's called a hypercube in R4. And usually the way to draw it is something like you draw an actual cube, and then you draw another cube which might be bigger and connect certain vertices. Unfortunately, the 2-dimensional picture of a hypercube is not completely precise, but you can Google this sort of pictures. And so vertices of this higher dimensional cube basically give you subsets of a set with n elements. Okay, so what about binomial coefficients? So let's take a certain, so we have still the same set 1 to n, and we have a certain subset A. And so I associated to it a certain code. F of A is a certain sequence. Let me call it actually A1 up to AN of zeros and ones. And then I actually can say that the cardinality of A, the number of elements there, is just sum of these indices, because each of them is 0 or 1, depending on whether the element is there or not. So the sum of them just counts the number of elements in A. To n. Perfect. So now definition, which probably a lot of you know, is that so for k less or equals than n greater or equals than 0, so n choose k is a number of subsets of size k in a set of size n. So and if you want to think of it intuitively, that's the number of ways you can choose k elements out of a set with n elements. So imagine you have, for instance, 4 elephants, and you want to choose 2 of them. And then you need to pick one of them. There are 4 choices for that, and one of the remaining. So there are 3 more options, so 12 in total. But then your elephants become ordered. There is a first one and second, and you need to divide by 2 because you count every subset of elephant twice. So this gives you 6. And in general, so a little proposition is that there is a formula. So n choose k is equal to n factorial divided by k factorial n minus k factorial. So how to prove something like that? So of course there are tons of different ways, but the easiest probably way is to rewrite it in the following way. So consider the number n choose k times k factorial. So n choose k is supposed to be the number of subsets of size k, and times k factorial means that we choose this subset and then we order the elements, because remember k factorial is number of permutations, so number of ways to permute them, and so this gives you a number of subsets of size k plus orderings of their elements. But on the other hand, you can compute the same thing in a different way. So how to choose k elements and order them? That's the same thing as choose the first one, then the second one, then and so on up to the last one, and I in total subtract n minus k plus 1, multiply k times k numbers, and in this way I have chosen the subset of size k, and also the elements there are ordered, first, second, third, and so on. And of course that's the same as n factorial divided by n minus k factorial, and this gives the proof. So there are a couple of conventions. Remember that n choose 0 is 1, and that's consistent with the fact that there is exactly one subset of size 0, which is empty set. And that's the same as n choose n. There exists exactly one subset of size n. And for other numbers, these things are bigger. Okay, so that's the important fact. And then maybe there is another interesting observation, and this is that these numbers are symmetric in a certain sense. So n choose k equals n choose n minus k. And again, it's really simple to see, because in this formula, for instance, if you exchange k with n minus k, the nominator won't change, and here these two factors will interchange. So that's obvious from the formula, but one can also prove it in a different way. So let me prove it. And the proof is a bijection. So these are cardinalities of two sets. So we have number of subsets of size k, and that's one thing. And we want to show that this is the same as number of subsets of size n minus k. And one way to show it is to construct a bijection between the sets themselves. So suppose I have a subset A inside S of size k. How to construct a subset of size n minus k? So that's very simple. So you just take it and you send it to a subset which is just the complement. So if you take all elements except those in A, this will be exactly of size n minus k. And this is a map, and to see that this is a bijection, the easiest way is to go backwards. If you take a subset of size n minus k and take the complement, you get a subset of size k. And these are two kind of mutually inverse maps, as we discussed in the lecture 2. And so in this way you can easily prove that these two numbers are equal and these two sets are in a bijection. Okay. So this formula is not very practical, because it actually gives you, I mean, you can compute with it, but it requires a lot of multiplication, division, and other stuff. So there is a simpler way to compute these numbers based on a certain inductive definition. Let me do it right now. Okay, so proposition. Proposition. So n choose k equals to n minus 1 choose k minus 1 plus n minus 1 choose k. And again, there are tons of ways to prove it. So proof, and maybe the first one is use the formula. And that becomes a very simple exercise. So basically one gets n minus k plus k is equal to n, more or less. So very simple, simple proof. But there is another way to prove it. So maybe more conceptually. So let's look at all this parts. So consider, so we have this subset S of size n. And then we have a set of its subsets. So this is a set of subsets of S of size k. So this is the number we want to compute. And then we can just divide them in two parts. So one part are subsets A such that A contains n, the last element. And here subsets A such that A don't contain n. So, okay. And of course, the number of elements in the whole set of subsets of size k can be split into two parts. So the number of subsets not containing A is the number of subsets containing n. So how many subsets are there not containing n? So this thing is in bijection. So subsets not containing n, you can just forget about n, and this will be subsets of the same size inside a set A S without n. So this is in bijection with subsets of size k in the set S without n. And of course, the cardinality of this one is exactly n minus 1 choose k. But on the other hand, if you look at this set, that's also in bijection with subsets, but now of size n, k minus 1 in S without n. And the reason is because if you have certain subset A, you can just send it to a subset where you take A without n. And this is a smaller subset of size k minus 1 of the smaller set. And of course, this set of such subsets has cardinality n minus 1, k minus 1. So this is the recursive definition, and one can use it. And the usual way to picture it is to just draw all these binomial coefficients one under the other. So 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2. So I draw a certain triangle, which is called Pascal triangle. And in each row, I draw all binomial coefficients, so all numbers of subsets of certain sizes. And why you do that? So the beautiful kind of fact is that what it means that each element here is exactly the sum of two previous elements in the previous line to the left and to the right. And here I think that sort of it's surrounded by a huge sea of zeros. So everything kind of beyond to the left and right of this triangle consists of zeros. And so yeah, and the formula still holds. And also 0, 0 is by convention 1. Kind of one subset of size 0 inside the empty set, which is empty set. Actually makes sense. And if I just compute it, I will get this famous Pascal triangle 1, 1, 1, 1, 2, 1. So I just sum up elements to the left and to the right of the next row element. So 3 is 1 plus 2, 3 is 2 plus 1, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 6, 15, 6, 1, and so on. And you see it's super fast to compute, much faster than use this factorial formula. And also, if you look at this triangle, you immediately notice that it has an axis of symmetry. So we will talk about symmetries later in the course. And there is this flip mirror symmetry, which it is kind of invariant under. And of course, that's nothing but the fact that n choose k equals n choose n minus k. That's just exactly the fact that the Pascal triangle is symmetric. Okay, so now I want to talk about binomial formula, which is again probably known, but it's a very surprising fact in a sense, because we are talking about some combinatorics, and now I'm going to write down an algebraic identity which is kind of capturing this combinatorics and which gives additional meaning to it. Super important theorem. So theorem which is called binomial formula. And it is a statement that a plus b power n equals to n choose 0 a power n plus n choose 1 a power n minus 1b plus and so on plus n choose n b power n. Or if I want to write it more compactly, I will say sum n choose k a power k b n minus k from k equals 0 to n. So that's the famous binomial formula. And of course, the simplest cases, which you probably know by heart, is a plus b squared and a plus b cubed. Perfect. So how to prove it? So as you probably already know, when you see new and important mathematical facts, you will try to come up with as many proofs as possible. So the first one might be by induction, and it's actually a good exercise in induction. So you can just multiply it on a plus b and use the previous formula, this inductive formula. I'm not going to do it, but it's a good exercise if you are practicing with induction. Maybe more conceptually, so let's at least see like where this comes from, because there should be some reason, right? So why number of subsets is related to this opening brackets. So let's just write down a plus b power n as a product, a plus b times a plus b times a plus b n times. And then I just open all brackets, and I don't even add something up. I just get monomials. So I will get a sum of monomials, and monomials which I get, of course, will look like a b b a b a or something. And in each monomial, there will be a certain number of a's and b's. So, so this, of course, equals a k b n minus k. Basically, each monomial, so I will get each monomial by choosing a and b in one of the brackets. So I need to make a choice a or b, a or b, a or b, and so on. And if you compare it with the function we constructed from set of subsets to this cube, you can see that basically what I get is I need to choose 0 or 1 for each position, and like 0 corresponds to choosing A and 1 choosing B. And so that's the same thing as sum over all subsets A inside set 1 to n. And then I take A to the power cardinality of A, B to the power cardinality of S minus A. So this is S. So again, this is a slightly non-trivial step. So if you want to very carefully say what happens here is that basically you sum here over all points of this n-dimensional cube, 0, 1, power n, and for each point you take a or b depending on you get 0 or 1. And since the cube parameterizes subsets, then the same thing as summing over all subsets. But that's, of course, now we can apply the fact that we'll see the same monomial the number of times, which is a number of subsets of the certain cardinality. So this gives the right-hand side. Right-hand side. So basically, this is just a proof by opening the brackets. And I want to give maybe a corollary. So if I now plug in A equal to B equal to 1, I of course see that 2 power n equals to the sum of binomial coefficients. And that's just because a power anything, b power anything equals to 1, and a plus b power n is 2 power n. And notice that this kind of interesting identity now has a couple of proofs, because on one hand it follows from this binomial formula, on the other hand it follows just from interpretation, because these are subsets of all sizes, and this is the number of subsets in general. And also, you can, for instance, prove it by induction using the inductive formula. And in general, if you see an identity between binomial coefficients or some other combinatorial quantities, usually there are different ways to prove it. Some of them may be based on explicit bijections, as we already did a few times. Other can be based on induction and explicit formulas. Usually they are the least enlightening, because you don't, you prove it by opening brackets, but it does not explain why the magic happens. And lastly, there is a strange way to prove identities in combinatorics using certain algebra related to certain functions. So for instance, here I plug in a equal to b equal to 1 here and get the proof. And in the next lecture, we will talk about Fibonacci numbers and Catalan numbers after that, and we will find formulas for them using this kind of generating functions. So certain functions whose coefficients are when you present them as power series, are counting some combinatorial objects. So the next topic will be generating functions for Fibonacci numbers and for Catalan numbers.